Hey boys and girls, this is Mrs. Lewis. I am re-recording this for the third time, so if I talk a little fast, I'm sorry. I am re-recording chapter 1 for my physical science class because you will notice throughout the year that sometimes the notes follow along exactly with the video and sometimes they don't. That's because science is ever changing. When a science book becomes published and available to students and teachers, it is already 5 years out of date. Unlike math, unlike the Civil War, unlike so many things that you get in school, those things don't ever change. We might add to them, but they don't ever change. 1 plus 1 will always be 2 unless you're doing new math. In that case, the answer is 3. In science, however, it is constantly and consistently changing. What may be a planet today may not be a planet tomorrow, and so forth. So, because of that, I will be updating these videos as needed. If you find that it doesn't follow exactly like chapter 1 does, you will find the information if you watch the video in its entirety, anywhere from 5 minutes to 15. Never ever longer than a 15-minute video. Also, your book is another great resource. These note packets that you've been given, these are yours, ladies and gentlemen. Feel free to write all over them. I will advise you to put your name on it. I'm never going to collect it, but I guarantee people have accidentally had other people's notes. And the reason why it's important that you know where your notes are and that you can retrieve them if ever lost is because a lot of times, most of the time, I allow you to use your note packets on quizzes, and you will have anywhere from 1 to 3 pop quizzes every single week. So make notes, keep notes, watch your video lectures. Also, your note packet is a really great place to highlight. I like to doodle when I listen. I don't know why. Helps my little ADHD brain work. Also, you might find that you'll have questions for me or you don't understand a particular concept. Write it down on your note packet so that you can ask me in class and we can address it together, because chances are if you have the question, so do 6 other people. So moving on, section 1 of chapter 1, otherwise affectionately known as 1.1, the method of science. Essential questions are super important, and here's why. This is where I'm going to look. Did you learn what I needed you to learn from this particular section of this particular chapter? In science, I don't want to know the why. I mean, obviously, I want to know why. But I want to know that you know why the why is the why. Makes sense? I call it y to the 3rd power. But tell me why. Okay, but why? Can you explain your answer to me? And can you explain the explanation through examples, reasoning, and supporting it with evidence? So that's what I'm looking for, okay? Deep, thoughtful answers. Yes and no isn't going to fly in high school physical science. So make sure you're looking it up. If you can answer these 3 things in detail, you will do really well on the test 1.1. What steps do scientists often use to solve problems? Why do scientists use variables? And what is the difference between a scientific law and a scientific theory? And in your head, you should already be saying, but can I explain to her why and support it with at least 2 different examples? Science is not just a subject in school. It is a method for studying the natural world. After all, science comes from the Latin word scientia, which means knowledge. Science is a process based on inquiry that helps develop explanations about events in nature. Although scientists do not always follow a rigid set of steps, investigations often follow a general pattern. The pattern investigation procedures is called the scientific method. 6 common steps found in the scientific method are shown to your right. A scientist might add new steps, repeat some steps many times, or skip steps altogether. And I will tell you that scientific method, that phrase, is going out, and they have replaced it with engineering practices. So you may hear that being used interchangeably. To your right, you can see the different scientific method, and I do want to discuss this. Up to this point, and they weren't wrong, they were correct. We taught the scientific method in a linear fashion. Linear being first step, second step, third step, fourth step, and this is how we go. That's not like that anymore. It's more of a cylindrical pattern.
scientific method sucks. Now, by that, I don't mean that science sucks. As a physicist, I believe that science has had countless benefits for humanity. But when I was in 8th grade, I learned about this thing called the scientific method. And since then, I have done science, I have worked with other scientists, and I've taught science to college students, to K through 12 teachers, and to 7th and 8th graders, middle schoolers. And from these experiences, I've come to the conclusion that the scientific method sucks. If it's been a while for you, as it has been for me since middle school, let me run through it real quick for you. First of all, step 1, I did research. Step 3, form a hypothesis. Step 4, do an experiment with some independent and dependent variables to test your hypothesis. Step 5, analyze data. Step 6, draw a conclusion. It sounds good, right? It certainly matches what we see on TV and in movies and what we see on the news.
So I'm going to butt in here just a little bit, and I do this a lot. Warning, alert for students new to my class. A lot of times students will skip and fast forward, you know, the little 10-second button. Yeah, sometimes I put a built-in quiz in the videos every once in a while. You'll never know when I'm going to bust into one of these, so don't skip. Watch it in its entirety because you may miss something. I'm going to let you know now that you will still need to know the linear format of the scientific method. So memorize it.
Unfortunately, it completely misrepresents what scientists do and what science is all about. And this manifests in 4 main ways. First of all, it's incredibly linear. We start with a problem statement and we end with a conclusion. This implies that science is something that's once and done, fixed for all time. Secondly, it's not very intuitive. How do I choose a problem? What do I do with my conclusion when I'm done? If I have no idea what should or even could happen, how do I come up with a hypothesis? This makes the process intimidating and dangerous. 3, there's a focus on conclusion, reaching the conclusion, on getting a fact. Well, what happens when the information changes? What happens when facts change? How does this process capture that? And finally, the focus on experimentation. Now, don't get me wrong. I'm a big fan of teaching students to control for whatever random variables they can. But there's been a lot of really good science that's been done without being able to control for, well, anything. Create a laboratory.
Okay, so I'm going to break in here for a minute. When he said no controls, that's true in real world situations. But I will tell you, every single antibiotic you've ever been given, every painkiller you have ever taken, any type of steroid you've needed because you are severely allergic to poison ivy, I guarantee in order to have the approval from the Federal Department of Agriculture, FDA, you had to have, are you ready? A control. So for this school year and the rest of your time at West County, you will still need to show or find a control in your experiment. So although I am not disagreeing with what he's saying, I'm letting you know now, we will have controls.
As a culture, as a civilization, we fear science. Why? Well, I believe there are 3 main sources of that. First of all, we're obsessed with right answers. We're obsessed with conclusions. And as we go further and further, we learn more and more stuff. We can't keep track of it all. In addition, the facts, those conclusions, change. Let me give you an example. If you're like me, when you were growing up, there were 9 planets in the solar system. In 2006, one of these things was eliminated. Which brings me to my 3rd point. Why? We don't understand how these decisions get made. We don't understand the thought process behind it. Now, all of these problems possibly don't lie at the feet of the scientific method, but it's not helping. There is, however, a better way. Let me introduce you to the cycle of scientific thinking. This starts with interesting observations. What counts as interesting? Well, if you find yourself asking the question, what happened there? Why did that occur? What's going on? It's probably interesting. In the face of such questions, the human brain does an amazing thing. It tries to come up with an answer, a story, an explanation of what's going on. Now, a lot of people are perfectly happy to have an answer. And it's true, it is correct. Then I should also see this. They make a prediction. And once you have a prediction, the only thing left to do is to go make observations to see if you were right. And if you are, yay! But if you're not, if you're truly lucky and you got it wrong, then that's going to bring up more questions. Questions that require more explanation, which leads to new predictions. And so
sometimes scientists cannot see everything that they are testing, and they might be observing something that is too large or small, takes too much time to see completely, or is hazardous. In these cases, scientists use models. A model represents an idea, event, or object to help people better understand it. A scientific theory is an explanation of things or events based on knowledge gained from many observations and investigations. It's not a guess. I don't even like the word guess, and you'll learn that in class. If scientists repeat an investigation and the results always support the hypothesis, then the hypothesis can then be called a theory. We'll talk more about that later. A scientific law is a statement about what happens in nature and that seems to be true all the time. Laws describe specific relationships under given conditions. They don't explain why, and they don't explain how something happens. Gravity is an example of a scientific law. The law of gravity states that any one mass will attract another mass. To date, no experiments have been performed that disprove the law of gravity. There are limitations to everything, even my superpowers. Science can help you explain many things about the world, but it cannot explain or solve absolutely everything. Although it's the scientist's job to make guesses, the scientist also has to make sure his or her guesses can be tested and verified. Science can't answer all questions, such as questions about emotions and values. This piece of artwork might look very beautiful to one person and not really to another.